Here you see a fully developed stall in a diffuser with a divergence angle of about 45 degrees. Let's insert an assembly of vanes designed so that each passage lies below the line of first appreciable separation on our flow regime chart. When the vanes are removed, the stall comes back. It's often useful to use more than one method of visualization. Let's use another technique to look at some of the things we've seen before, and also to study a new pattern of flow regimes, laminar turbulent transition. For this purpose, a useful but very simple method is dye injection. All you need is a flask of adjustable height and a manifold with hypodermic injectors. Any dye can be used, provided its density is very close to that of the working fluid. Here you see the jet flow pattern made visible with streak lines of dye. Compare the pattern of the jet flow you see here with the bubble picture we saw earlier. The recirculating eddies, which you now see at the sides of the main flow, are made visible by seeping dye through holes in each wall. Dye must be injected with some care. If we apply the wrong pressure to the injectors, the dye will come out too fast or too slow. This causes jet instability, as you see here. Here's an apparatus to look at the flow very near the wall. The apparatus consists of a dye reservoir connected through a thin rectangular slit to the flow. The slit is only a few mils wide. The layers of flow extremely close to the wall are crucial in heat and mass transfer, in flow separation, and in the structure of the turbulent shear layer. The dye is turned on and seeps slowly through the slit. It moves upstream because the diffuser walls are at a very large angle and the flow is stalled. The walls are moved parallel. Now we are looking directly at the wall which contains the slit. The slit is near the left edge of the picture. Notice the smooth, almost glass-like appearance of the dye. This is typical of a laminar boundary layer. Now we introduce effective trips. The flow over the slit becomes turbulent. The relatively regular, streaky structure you see is typical of the wall layers of the turbulent boundary layer. The dye streaks are actually zones of low-speed flow, and the clear areas in between are faster-moving fluid. If we remove one of the trips, we can observe the transition region between laminar and turbulent flow over the slit. In this region, you can see laminar flow side by side with turbulent flow. You can also see transient spots of turbulence moving down through the flow. If we move the remaining trip further upstream, the fraction of the flow which is turbulent at the slit decreases. Finally, the entire flow becomes laminar again. In the laminar turbulent transition problem, we again find several patterns of flow, and again the state of knowledge is different for each pattern. If we know the flow is laminar, we can calculate many fine details of performance from well-developed theory. If we know the flow is turbulent, we have workable approximate theories for a few simple cases. In a number of other cases, we also have good data correlations for such things as friction and heat transfer coefficients. If the flow is in the transition region, the theory is quite incomplete. As in our diffuser example, theoretical prediction of when a shift will occur from one regime to another is the most difficult thing of all. We have only part of the theory for a handful of cases and data correlations for a few more. We can predict results based on established flow models, but even in this very old and much studied problem, we still need correlations of data to predict the flow pattern that will actually occur. Let's consider one more example. Here's a flat plate parallel to the flow. A laminar boundary layer builds up on each side and forms a small symmetric dent in the velocity profile. But the dent is not evened out by viscosity. As the flow goes downstream, the two boundary layers interact to build a large oscillation. Here's the same flow shown by a single bubble wire downstream. Once again, a steady, symmetric upstream flow leads to an unsteady oscillation in the downstream motion. To predict the behavior of real fluid flows, we need to know the actual flow patterns. Flow visualization is one effective way to find them.